My title of the topic is Next Generation Facility Optical Fiber for High Power Fiber Laser and Amplifier and Broadband Source. Basically, what I have actually chosen this topic because facility optical fiber is one of the important component for making of any fiber optics based component and device. And my outline of the topic is we will give some introduction of the facility optical fiber along with objective and some three different varieties of facility optical fiber. This facility optical fiber basis of the core composition base for basically for enhancement of the photo darkening resistivity of high power fiber laser. Another is the double plate erbium ytterbium multi-material composition based fiber for high power optical amplifier, and another is novel nanophase separated multi-element dope low silica content glass based bismuth dope fiber for broadband source, and finally come to the conclusion. Facility optical fiber basically is one kind of material base which have different composition or which have different waveguide design or which have different kind of coating material. So here we want to means facility optical fiber based on different material composition based core composition of optical fiber. If you see our periodic table, almost all of the elements have been still now used for making of the facility optical fiber for enhancement of their spectroscopic property for viewpoint of high power laser amplifier, optical amplifier. And if in 150 anniversary of the periodic table of the element, which held in 2019, highlight the tremendous role of this kind of element in chemistry, physics, biology, astronomy, engineering as a shining scientific breakthrough significantly in the field of glass and optical fiber. My objective is that development of multi-element nanophase separated fiber for high power laser to solve the problem of photodarkening phenomena, development of multi-element glass-based erbium ytterbium dope fiber to increase the radiation resistivity along with long-term stability of the output power for high power optical amplifier. Another is nanophase separated multi-element dope low silica content fiber which can be used as a broadband source starting from 1100 nanometer to 1600 nanometer, having output power greater than 100 milliwatt and flatness of the spectra less than plus minus 5 dB within 1100 to 1600 nanometer. And all these kind of fiber we have done material characterization, spectroscopy and other thing from viewpoint of fluorescence, amplification, AC nature and lasing property of the fiber. Basically, main challenge of the high power optical amplifier is that laser is that photo darkening phenomena. Then how we can solve this photo darkening phenomena by choosing the suitable composition based optical material to reduction of the conversion of ytterbium 3 to ytterbium 2 to improve the slope efficiency, laser output power and long-term stability. And basically what we have done basically aluminum and phosphorus fiber, and then we have reduced enhancement of the OH loss and also photodarkening phenomena, UV visible spectra and thermal annealing. If we see the photodarkening, there is basically what is happening. This is basically one kind of structure, nanocrystal structure that can promote shifting of the lone electron to the nearest neighboring non-meeting oxygen atom which is bonded to ytterbium ion and into positive charge vacancy which carry the nanocrystal and produce under high power pump power. And in this way, this shifting can be prevented by choosing of suitable composition which can reduce the concentration of ytterbium 2 ion and from viewpoint to reduce the photodarkening effect. And basically what we have used phosphorus, zirconia, cerium, aluminum, calcium, dope fiber along with their different kind of role. And phosphorus basically to increase the nucleation goal, ytterbium for increase the basically for active performance of the fiber from lasing, zirconia chemical stability, cerium basically used to reduce the formation of ytterbium 3 to ytterbium 2 ion, aluminum increase the basically to increase the solubility, and calcium oxide to stabilize the ytterbium 3 ion under high power application. And this is the basically general procedure how we have flow. This is the solution doping process, and along with MCBD, we deposit the phosphoro germanium silica layer, then we make a solution doping, and then we give the dehydration oxidation, then we dot the preform, and then after fabrication of the preform, we go to annealing. And annealing process is very important for generation of the nanocrystal within the core of the fiber. And this nanocrystal basically prevent the formation of ytterbium 2 ion from viewpoint enhancement of the photodarkening effect. And this is the basically hexagonal geometrical fiber. And if we see the temp spectra, this is basically enhancement of the nanocrystal, which is basically in the size of 7 to 10 nanometer. And this is the basically we have compare standard ytterbium fiber and multi-element of ytterbium fiber having the same concentration from viewpoint of the same absorption, cladding absorption in terms of dB per meter. And if we see the performance of the lasing performance, what we see, we have compared both the standard ytterbium fiber and multi-element doped fiber. This is the basically multi-element doped fiber, and this is the standard ytterbium doped fiber. In this case, we have used same length 5 meter and launch pump power 50 watt and give 73.0 watt output power. And slope efficiency for multi-element ytterbium doped fiber is much better. It is around 76% compared to newfound standard fiber. And we have also measured the photodarkening effect. And if we see this curve, in 633 nanometer wavelength is used for photodarkening phenomena. 1 to 2 centimeter lens we use. And if we see the photodarkening, this is the curve with respect to the time. This must enhance with respect to the standard ytterbium doped fiber. So this indicates that this kind of multi-element doped fiber ytterbium will be useful for hyper-optical lasing to reduce the photodarkening effect. And this is the basically conclusion of the multi-element doped fiber. This include phosphorus, zirconia, cerium, aluminum, and calcium nanophase separated fiber for use of a high power laser to solve the problem of photodarkening. And the nanophase separated is generated 7 to 10 nanometer reach in ytterbium, because higher size will give rise to high loss, scattering loss, and obtain 76% engineering efficiency, 37.5 output power. And this kind of fiber is become very much photodarkening resistant compared to standard aluminum phosphorus doped ytterbium doped fiber. Now come to the second point. This is another new kind of fiber we have developed. This is erbium ytterbium doped fiber for hyper optical amplifier. And in this case, we have used phosphorus, aluminum, germanium, cerium, boron, and thorium. And each of these elements have some role for basically from viewpoint of enhancement of the radiation hardness of the fiber for use of this fiber for satellite communication system. Here, fluorine dope is used to increase the radiation hardness. Cerium is used to prevent the ytterbium related defect center. Phosphorus aluminum to enhancement of the solubility of erbium ytterbium. And aluminum also is used, but that can be minimized because aluminum oxygen hole center also create, which gives rise to basically reduce the performance of the optical amplifier. Boron and phosphorus also enhance for transfer of the efficiency from ytterbium to erbium and reducing the fluorescent lifetime of 4 by 11 by 2 level of erbium. And another important parameter is the ytterbium-erbium ratio. This ytterbium-erbium ratio is very vital to prevent the assembling of ytterbium ion at 1 micron region. And this is the basic scale for making of this kind of fiber. This is MCBD solution doping technique, and we have deposited fluorine dope phosphosilical layer, and then this layer was soaked with a solution of erbium chloride, ytterbium chloride, aluminum chloride, cerium chloride, and boric acid, and then proceed to dehydration, oxidation, collapsing, and finally make a annealing of the dough, and then finally converted to octagonal shape fiber and then to the fiber with low Ri resin coating. The main important parameter is that phosphorus doping should be 22 to 23%, erbium oxide 0.5 to 0.75, ytterbium 7.5 to 9, and ytterbium erbium ratio will optimize 7.5 to 11. And this kind of optimization reduce the back energy transfer from erbium to ytterbium ion to optimization of the ratio. And minimization of the evaporation of phosphorus is also very important to reduce this evaporation. Otherwise, the photon energy of the center portion of the erbium ytterbium ion will be different than that of the surrounding other portion. And this is the normal procedure. We have already explained how to make this kind of fiber by solution doping process using different kind of element into the core matrix. And this is the P-form we have made, and this is the fiber. This is the octagonal shape having different diameter of the core. And this is the refractive index profile for making of this kind of fiber, having around 0.17 to 0.2 Na. And this is the EPMA curve. This is very important for elemental distribution of different dopant, how it was distributed along the diameter of the core. This is a fluorine, erbium, ytterbium, boron, cerium, germanium, phosphorus, aluminum. This is the distribution of different element along the diameter of the fiber. This is very important for getting the performance of the fiber from viewpoint of uniform distribution of the different dopant along the core of the fiber. This is basically core absorption and cladding absorption. Cladding absorption basically around what we have maintained 40 to 50 dB per meter, and core absorption around 40 to 750 dB per meter, around 1550 nanometer. And now the question comes, if we go to increase the phosphorus doping content, photon energy will be decreased and performance will be increased. Performance will be increased means the back transfer energy from erbium to ytterbium will be prevented. But we cannot increase too much. Here we have seen some result where we increase the phosphorus doping 25%, it gives rise to phase separated glass. And this phase separated glass drastically reduce the performance of the fiber and also induce the self-ledging of the ytterbium. And this is the self-ledging phenomena. If we increase the pump, give the emission, after certain pump power, then ytterbium started the ledging. So this is a very vital point to prevent the basically ytterbium self-ledging in case of erbium ytterbium dope fiber. And how to manage? If we ytterbium erbium ratio should be vital. If ytterbium is present in excess, that means excess means non-participant ytterbium. If non-participant ytterbium gives rise to self-ledging phenomena and under pumping at 94 nanometer. As soon as self-ledging phenomena started, drastically 1550 nanometer performance of the amplifier will be reduced. And we have also measured the fluorescence lifetime measurement of different fiber with increasing the basically phosphorus doping level, and here phosphorus is increases and fluorescence lifetime of 4/11/2 level gradually decrease. And see, on the other hand, the 4I/13/2 fluorescence lifetime increase, and but ytterbium fluorescence lifetime 2F/F5/2 basically almost remain the same. That means if we increase the fluorescent phosphorus content, photon energy gradually decrease and amplification performance of the fiber will be increased. Another important performance of this kind of fiber is that radiation hardened. We have measured the cobalt-60 gamma radiation source used to see the performance of the output power and optical gain. And here we have seen that this kind of fiber 35 give the best performance. Here the basically the gain performance we have used 1.25 mega electron volt of the energy, and we have increased the radiation up to 5.7 kilorad. And in this case 35, this fiber contains cerium, where cerium doping prevent the formation of phosphorus induced center as well as ytterbium 2 ion. For this kind of fiber, can be used for a radiation hardened fiber for hyper optical amplifier. And if we see the gain, then this fiber gain is much less decreased compared to cerium less fiber. And in this case, the best performance is found 0.1 dB per kilorad in this case. And also we have studied the resin performance. If the resin performance is also very important for high power, because for high power the heat energy will be generated, and how much heat can be sustained this kind of low RI resin. We have measured that up to 245 degrees centigrade this fiber can sustain, because after 245 drastically the weight loss of the lower eye pure lower eye resin is drastically decreased. And we have measured the output power with respect to signal power amplification, and also we measured the increase the output power with respect to the wavelength. This is the basically 1550, and we also measured the basically AAC curve of the ytterbium self lasing. Here lasing is not start, but AAC started. So this fiber is very important from viewpoint of hyper amplifier. And similar another fiber, we also measured the output power with variation of the signal power for 0.5 to 2.5 watt, and also measured the lasing of the output power, and also measured the gain with respect to signal power with variation of the signal power for 5 minus 10 to plus 10, and also another also noise figure you also measure. Noise figure is around less than some of the fiber less than 5, and gain we have also achieved around 28 29. This is also another fiber. And we have also studied the long-term stability of the EDFA module to see the performance of the fiber. We have measured almost running the 4 months for 10 watt output power of the switch, and power less reduction is less than 2%. And another we have tested 15 watt, and we have measured very negligible actually reduction of the output power of the running of more than 150 hour for running the module. And this is the basically we have developed this kind of EDFA module for phase communication, leader, fiber to home, and phi communication purpose using this kind of patented multi-element of erbium radiation hardened fiber. So final conclusion of this amplifier is that we have developed multi-material based erbium doped fiber which show excellent performance, and which also give rise to 15 to 18 hour long-term stability output power, and also prevent the self lasing. And we have measured the gain variation is 0.1 dB per kilorad with less than 10% reduction of the output power after total cumulative dose of 6 kilorad. And also we measured the stability of the long-term stability. It is less than 2% for running of the more than 3 months of the module. And we have also some commercialized this kind of module with some industry, and also this kind of amplifier will be used for FTT. Let's come to the one kind of fiber we have developed. This can be used Bismuth multi-element nanophase separated fiber, which can be used for a broadband AC source starting from 1100 to 1600. The best technique is that here we deposit phosphorus germanium dope layer, and we incorporated aluminum, bismuth, lead, gallium. This is a basically high molecular weight element, and we have maintained the basically viscosity 25 to 26 centipoise, and also we have deposit this layer which have 60 to 70% porosity. And after that, what we have done, we have making this kind of preform, we go to thermal annealing at 1200 degrees centigrade for 2 hours, and cooling and heating rate of 5 degrees centigrade per minute to generate 5 to 10 nanometer of phase separated particle. And from this anneal preform we draw the fiber, and we have, so by this process we are able low silica content glass based fiber, where the silica content is around 20 to 25 weight percent. And this we have our patented, and we have shown that this kind of fiber also give unsaturable, low unsaturable loss, 0.6 to 1.5 dB per meter, which is around 25 to 30 percent of the total signal absorption. And we have measured also the AC power. It is more than 100 milliwatt, having flatness less than plus minus 5 dB. And this is a different kind of 3 fiber, and this is the different content. And here you see the silica content 21.5 to 26. This is the beauty of this kind of technology, of this kind of fiber, where we are able to make not other low melting glass, we are able to make basically for solution doping process, where we have used the saturated, non-saturated solution, and solution doping is not done at normal temperature, it is done around 65 to 70 degrees centigrade. And this is the whole the basic process of the how to make the preform fiber and then finally drawing. And this is the preform low silica content cross section, high resolution team, microscopic view, EPMA curve, reflective index profile, loss curve of the fiber, and unsaturated loss curve fiber with variation of the pump per 1064. And this is the final AC curve. This is the one of the fiber, 2 fiber we have measured. This is flatness almost starting from 1100 to 1600 nanometer, and output power 115, and input power we have given 4.8 watt, and but the length is around 20 meter. Hot bismuth fiber basically use more than 100 meter people are using, but here we have used only 20 meter fiber, this kind of low silica gas fiber. And this is the basically whole the process, technology process, patented process, how we can be done. This is the solution, beauty of this process. Solution doping is done 70 degrees centigrade, and super saturated solution we have used, where the normal, we are not used the normal solution at room temperature. By this way, we are able to make low silica content glass gas fiber, and after that we make the annealing, and then we get the nano engineering bismuth fiber for making of the AC source. And this is the whole process. This is the basically porous layer, and porous layer is around thickness 10 to 11 micrometer, and this is the cross section view of the basically microscopic axial direction, where the porosity is 65%, so that the more amount of dopant can be incorporated into the glass to reduce the silica content. And this is the basically supersaturated solution, and this is the preform, and is the collapsing, and then this is the chamber where we have done solution doping at 70 degrees centigrade. And this is the whole process of the annealing, how to make the preform can be annealing, and to make the phase separated particle. And there is also reflective index profile and distribution. Beauty is that by this process we are able to make uniform distribution all the elements, starting from aluminum, germanium, phosphorus, bismuth, lead, and gallium, uniformly doped. And this is the basically we have measured the TEM analysis in case of fiber, because fiber TEM analysis of the fiber is very, very difficult, because here the code dimension is 10 to 11 micron. So in this case we have optimized the collapsing annealing conditions so that the nanocrystal come to around 8 to 10 nanometer range. And this is the basically loss curve, this is the absorption loss curve, this is the unsaturation loss curve. And this is the what is happened, this fiber basically before annealing, what before done and then done the fiber. But in this case, preform, after fabrication preform, we go to annealing to make a phase separated region, and then dot the fiber, and enhancement of the intensity is increased in both cases. This is also the same curve what we have shown. This curve gives the best result for uniform flatness of the AC spectra. And final conclusion is that we have nanophase separated multi-element Bismuth fiber we have used, developed, and which can be used for a broadband source starting from 1100 to 1600 nanometer. And first time we are able to make low silica content glass based fiber by MCBD solution doping technique. And in this way, we have optimized the porosity of the layer 60 to 70%, thickness 8 to 10 micron, and using supersaturated solution 65 to 70. And also we have used special kinds of solution doping chamber where the doping is done at 65 to 70. After that, we go to annealing, and annealing is done 1200 to 1250 at a heating cooling rate of 5 degrees centigrade per minute to generate nanophase separated particle 5 to 10 nanometer. And this kind of fiber show emission 1100 to 1600 nanometer under pumping 1074. What people are doing at around basically 1200 to 1300 nanometer for bismuth doped fiber. Here we are able to make this kind of AC 1074 ytterbium doped laser and getting the flatness less than plus minus 5 dB of the broadband AC source, which can be used for bioimaging and optical amplifier. And I also acknowledge our fiber optic photonics group and Mexico CIO, fiber optics group, University of Malaysia, laser and fiber electronics group, Warsaw University, Poland, Naval Research Institute for Kochi, Department of Science and Technology of our India funding agency, and our Council of Scientific Research, Research Council, New Delhi. Thank you very much for your question.